When we study dynamics, we use the idea of a system to help us with our frame of reference when we talked about what masses we had forces acting upon. We could have forces acting on a single atom, or we could have it acting on the finger of a single person, or we could have it acting on that whole person. Regardless, when we define that system, we defined everything in that system to be the mass when we talked about Newton's second law. Well, when we talk about energy, the idea of a system takes on another dimension. And that dimension is going to have a lot to do with something that we studied in chemistry, the first law of thermodynamics, which states that energy cannot be created or destroyed. So energy cannot be created or destroyed. It only changes form. That idea is known as the conservation of energy. But what is energy? We can define energy as the measure of a system's capacity for doing work. Although, if we remember, when we learned about entropy, some of that energy is actually unavailable for work because it's locked up in useless heat or it's spread out too thin. But theoretically, if we could get all of that stuff back in order, back in line, it could once again do work. And so when we look at energy, we're really looking at what's in the system. And so when we talk about systems in energy, there are three types. We differentiate these different types of systems by what they allow to pass in and out of them between the system and the environment. An open system can move both matter and energy between it and its environment. A fantastic example of an open system is people. People eat food, so they're exchanging that matter with their environment, and they can also absorb and release heat, and they can do work to their environment. And so we would be considered an open system. A closed system could also be considered a sealed system. This is going to be a system where energy is able to move in and out of the system, but matter does not. What's an example of this? Well, a good example of this could be just any sealed container. Think of a bottle of water. You leave it sit out on the counter and it will steadily rise to room temperature even if it's been in the freezer for hours. It'll get up to that temperature because energy is able to move in and out of that water. However, the water itself stays in that sealed container. Our final system is an isolated system where no energy or matter may pass. This is going to be a system that is unable to interact with its environment. And so we can see here that we really have two things that can move in and out of a system. That's matter and energy. In an isolated system, we could consider this to be impossible. Just based on these definitions, we might be able to identify that an isolated system, a truly isolated system, is physically impossible. There will always be some amount of energy or matter that could pass through. But engineers trying to construct better and better insulation, things like that, might be trying to approach an isolated system. This would be the ideal. If we could make a house an isolated system, you could heat it once, and as long as you don't open any doors or windows, you never need to heat it again. It would stay that temperature. Now, while an open and a closed system are both possible, an isolated system is physically impossible. There is no way for us to truly isolate a system from its environment. After all, we can have galaxies that are trillions upon trillions of light years away from each other, but eventually they could run into each other and interact, and suddenly they aren't an isolated system anymore. And so an isolated system is a potentially temporary designation, or really more of considered an ideal scenario for the purpose of calculations in engineering. We might be trying to construct a thermos that keeps things cold or hot for as long as possible, and we might want to do some calculations considering it an isolated system to start to get an idea of what we would need to accomplish to get closer to that. So in physics, it can be really useful to think of these ideal scenarios that, while technically physically impossible, we can still do calculations and get as close as we can. Maybe get an asymptote towards that. But when we're working on energy, just to start out with, a lot of our problems are going to consider our environment and our system to be isolated so that there will be no net energy lost. And so if I have something like a ball that's above the earth, well, that ball has gravitational potential energy. And if I drop it, it'll fall. And it'll fall with a certain velocity. It'll steadily speed up until it hits the ground. Well, when it hits the ground, it might bounce back up. If it didn't lose any energy to its surroundings, it would bounce back up to the same height. Now, obviously, we know that if you've ever dropped a ball, you see that it doesn't bounce back to the exact same height. You need to put some more energy into it. But when we start to make these calculations, these are the things that we're going to kind of overlook so that we can just keep our calculations a little more clean. Now, when we are looking at AP Physics, AP Physics really only designates two systems. It says an open system, I'm going to put this in red. An open system freely moves energy, and a closed system does not. It doesn't really take into account the matter part of this. So just keep that in mind as we go forward. So as we are looking at energy, the main point we made there, the big point in our definition was that energy is the capacity to do work. So what is work? In physics, work has a very specific definition, and this is going to be the force applied on a system multiplied by a distance that force is applied for. So if I have a box that I push along the floor that I apply a force to, and I apply that force over a certain amount of distance, I have put energy into that system. And now that box, at this point, when I get over here, that box would now possess energy. So I would be considered the environment and I would be doing work on that box. So energy would be coming into the environment. So another way we can think of work is energy into the environment. That box might then do some work on another box. Maybe it runs into a shorter box and that box then moves forward and they have a collision, they collide for a certain amount of distance, yada, yada, yada. Well, then that box would have done work to this other box. Now this box would be losing energy. So its energy out would be going into this other box, which would then get an energy in. And so work is our way of saying energy coming into a system or going out of a system. Either work is being done on that system or it is doing work on another system. And we'll talk about later on if that work it does is considered useless and is lost as heat. However, for now, we're just going to consider this being work in, work out. So our work is our first equation in energy. Work equals force times distance, and work is measured in joules. Joules are represented by a capital J. Now, there are two types of energy that we're going to talk about right off the bat. And those types of energy are kinetic energy, just regular old kinetic energy, and potential energy. And we have official designations for these. So instead of writing KE or PE, kinetic energy is a capital K. And PE is a capital, Lord knows why, a capital U. Kinetic energy is going to be defined as 1/2 mv squared. And potential energy is going to be defined as mgh. This should make sense because if we think of potential energy is going to be what kind of work? If I've got a ball in the air, let's say it's at a height of h, maybe that's 2 meters, maybe that's 5 meters. It has the capacity, it has the potential to fall. And if it fell, the force of gravity would do work on it. And that work would last for a distance equal to its height. Well, the force of gravity is mg, and since that distance is h, we can say mgh. So the potential work that gravity could do would be mgh. Now, we have seen this before. Let's think back to kinematics. We had that combined equation, v squared equals v naught squared plus 2a delta x. We could really consider delta x to be a distance. And we could say a, that acceleration, would be 1 part of F equals ma. So if we took that times a mass, we would be left with work. We would have the definition of work. Well, that's what's happening here as well. mgh, that's that mad, or that a delta x. Well, our v squared is equal to 2 times that, so if we're defining our work as 1 times that, then we have to divide v squared by 2. And that's exactly what we see in the kinetic energy. We have 1/2 of that v squared, and then we just multiply it by mass, and we get energy. So these are the first 3 equations that we're going to be starting with. We're going to have work equals force times distance. We're going to have kinetic energy equaling 1/2 mv squared, and we're going to have potential energy equaling mgh. Now, one more important point. We have work, we have kinetic energy, we have potential energy. Do any of these have a direction? Energy is a scalar quantity. However, if we look at our work definition, force times distance, those are both vectors. And so when we multiply vectors like this together, one thing we need to consider is, how do they go together? Do we get a new direction? Does it matter if they're going in the same direction? And in this case, it does. When that happens, when we have, let's say we've got a force going this way and a distance going this way, only the force that aligns with that distance is going to count as work. And so we could say only that force times that distance is going to count as work. And so we can really say work equals force times distance times the cosine of theta. And then work would become a scalar quantity. When we have a situation like that, we call it a dot product, as opposed to other types of products of vectors. We're multiplying these 2 vectors together, but we're only considering the part of those vectors that actually overlap with each other. And so once we do that, we get a scalar out of that. In that specific situation, we call it a dot product. You will likely never see this terminology again, but we do need to be aware that if I have a box that gets lifted up, a force is applied countering gravity, and then that box is moved a distance, I do not consider any work to be done on that box. The force is upwards, the distance is sideways. And so my force times my distance times cosine of 90 would all equal 0. So that should serve us as a basic introduction to energy. We're going to start using these equations in order to make conversions in energy. And the way we're going to do that is through that first law of thermodynamics, where energy is conserved. If I do work on a system, the energy that came about from that, the energy that's now in that system, is going to stay there until that system either does work or loses that energy as heat. And so unless you are told that it loses energy, we will consider that it keeps all of its energy. At that point, the energy is just going to convert back and forth between kinetic and potential. As long as the energy stays in that system, it's going to be in one of those 2 forms. And it's going to be moving back and forth. Maybe sometimes it'll be half and half. Maybe it'll all turn into kinetic. Maybe it'll go up a ramp and then all be potential. But we'll look at this in practice problems and we'll see that unless we define where the energy is going, it stays put.